I guess I'll start off with a quick introduction.
Thank you.
Yep. All right. So yeah, thanks a lot, everyone, for coming back to the last session of the workshop. And kind of to start us off, we're really happy to have Lena Lee from Harvard, who's going to tell us about learning localized policies for multi-agent systems. So I guess I'll go ahead and let you take it away, Lena.
Great. Thank you. Thank you for the introduction. And thank you for organizing the workshop. It's a great pleasure to share some of our recent work on RL for multi-agent systems. So I've been learning a lot from the talks in the past few days, and they cover so many different aspects of multi-agent RL. So my talk will have some overlap with other talks, but hope the talk can add some new perspectives, especially through the angle of several physical systems. So since I only signed up for 30-minute talk, I will only give very quick motivation on the big picture. So my research background was on the control and optimization for societal network systems. So what's really happening in the past decades for these systems is that our society has been installing more and more smart connected devices, which are capable of sensing, communication, and computation. So with this data generated by the devices and with our advances in learning, we start visualizing smart systems such as smart houses, smart transportation, smart manufacturing, smart power grids. And personally, I've been working on smart grid for more than a decade. But always there's a kind of one question when we try to putting ourselves into a nice picture is, do more IoT or smart devices really mean that we can bring the AI success to the societal systems to make them smarter? So then once we look into the news, look into the reality, it doesn't take us long to realize that we are only at the beginning stage of transforming the societal systems to the future ones. So for the power grids, every time when we face extreme weather conditions, such as the winter storm or the heat wave, the solution that the power systems turns to are always performing rolling blackout, affecting many people's daily life. And then for the transportation, so firstly, it remains challenging to ensure safety under complex situation for autonomous driving. But secondly, even if we solve the safety issue for autonomous driving, it is unclear how to put these technologies together to reduce the traffic jams and improving our mobility. So what's the reason for the state of art of these smart systems? So one of the major reason is that learning for the physical, societal, dynamical system is very challenging. So now let's take a deeper look at the future smart systems from a control perspective. So what's happening right now is that we have more and more sensors that spread out in the systems. The sensors can monitor the local situations in real time and pass the data to either the edge devices or the data centers. So the data is shared among devices and processed by advanced algorithms. Decisions will be made and passed to the actuators. But so like this picture fits into the standard control feedback loop nicely, but the key differences are the following. So first of all, the sensors and actuators are in a huge number and they are spread out, located at different locations, generating a huge amount of data at all the different locations. So on the one hand, we have faster computation and communication tools, but on the other hand, all these technologies are still limited compared with the scale of the system. Moreover, so once we really going to connect all the active devices, they keep generating random fluctuations into the system, making the system become more and more complex and harder to model. Like all these challenges motivated people going to look at how about the data-driven decision-making tools. So like recently, the data-driven tools that people can call reinforcement learning or data-driven like learning-based control has motivated a lot of interdisciplinary collaborations. And in particular, reinforcement learning has brought control and learning communities together. So we have seen many remarkable successes about RL in areas such as Go, video games, and robotics. However, when we look into the technologies behind the exciting news, we see immediate challenges in using this method for the real-world large-scale societal system that I have been showing before. So first of all the methods require a huge amount of computation and simulation behind the result. It's hard to scale up to the large system in real time. Secondly, it is often challenging to provide theoretical guarantees on hard performance, such as stability, robustness, safety, and other conditions that we really care about for the physical systems. So with this kind of motivation, like we try to, when we start working on this problem, we're trying to think, like, can we even develop some scalable method for those multi-agent societal networks and still have some provable guarantees? So I'm going to show like some stories that some success stories that we have. But the key is this: it's not really just going to treat in the online dynamical system as just a black box. It's still going to use some knowledges we have the systems and trying to develop the method. So after that, I will actually spend a few minutes to come back to discuss the solution that we have is what exactly the problems that we really learned. So let me dive into the first part. If you have questions, feel free to stop me anytime. Now, let's dive into the model. So as I mentioned, the motivation for this work is motivated by societal network systems. So we go ahead to model those elements in abstract way, but still capturing some essential component. So in this model, like first we have the time, like this kind of the real, think about the online control, like online situation. So we have the real time stage here. And we have the state, like for each individual agent. So one difference is I think compared with other talks, we have been listening to other multi-agent talks is here. So here I introduce the state for individual nodes, individual agent. So for the power system, you can think about each agent, the nodes, as kind of one bus in the system. And for the transportation, you can think about as like each road condition or some other condition. I have some concrete example later. So now I have the individual state for individual agent. So for individual agent, they can take in actions. That's kind of mentioned. I have a sensors, I have actuators. So these actuators can take in local actions. So for the technical part, for this talk, I will focus on the finite state, finite action, like the tabular case. So there's a state transition. So what defines the network? So the network in here, let me go through it. It means for each agent, his future state will depend on his prior state and also his neighboring state and his own actions. So once you look at this local state transition rule, what it says is actually defining some network, right? What the network, the link here means is if one agent state can affect another agent's state, that means they are connected. So here the link of the network means they can affect the state transition for the other agents. So if question, feel free to ask me for this one. And for here, as I put in those examples, I said like the system just getting more and more complex. It's very hard to really have a model to really model how the state transition really affect each other. So we are assuming the state transition exactly what the PI, we do not know. But one assumption we're going to assume is overall, because I kind of know how the network is connected. So I know the connectivity of the network. It's just I don't know specifically what's the PI for individual link. And then we have a stage reward. And for the reward, again, we kind of assuming for each agent, he can observe what's going on locally, and he has his local evaluation of how good the situation is. That's kind of the local reward for the RI. And the control policy, I will come back to talk about what control policy we really want to learn. So not just at a high level, right? The control policy is just taking based on the state, taking an action. And A and pi here, kind of a joint action, come back to what kind of policy we really want to have. So the objective here is I want to find a policy that's going to maximize the long-term reward. And the long-term reward is a summation of everyone's reward over the infinite time. And I have the discounting reward case here. So I want to say the result have been extended to the infinite time horizon case, but I will focus on the discounting reward case to give you the intuition and idea. Now, let me recap. The essential part I want to highlight is the local interaction. So I have the start with the local interaction. And I would like developing some learning rule to learn some kind of policies to maximize the long-term reward. And I was just thinking about like this is different from the other talks, which talking about the games. Here I start with the cooperative setting. Like I just like every agent is kind of like the same actuator, it's kind of engineering component. I can engineering them, ask them to follow certain kind of learning rules. And I would like to making sure eventually I can solve the system, like achieve some global good performance. So this kind of essential component here, feel free to stop me if you have questions. So now let me give you a specific example, right? Where those kind of things come from. So first, if you think about epidemic, so we have been like in the pandemic for past 2 weeks, more than 2 years. So like the probability of one agent getting affected? Well, depending on the neighbors, right? Who are the friends we interact with? And definitely the one setting my model didn't capture is right now, I assuming the network structure is kind of fixed. So in this scenario, the network structure can be time varying and like the weight will be also changing. And that's like one of the future work we're probably trying to extend. And another one, as I mentioned, the transportation. For transportation system, what you can think about the state is the congestion of a road. So, and then for the congestion of a road, depends on the congestion of the nearby roads. And that's where the local interaction comes from. And you actually can think about many other examples. You will find like the local interaction is actually very like common in many network systems. So now let's talk about the challenges. So I think in the previous like past few days, we have been seeing like a lot of talk trying to address the curse of dimensionality. And in there, that's the first challenge we're going to face. And the one difference here is I introduced an individual state of the individual agent. So the curse of dimensionality is not just about the action, also the state dimension. It will quickly blow up as I have more number of agents. Now, there's another challenge is actually mostly come from like when I was thinking about how I'm going to really apply whatever policy I learned. So second challenge come from here. So let's suppose this is kind of the global view, right? I have this certain kind of magical learner and learn the good policy, and that policy will specify the relationship, the mapping from the state. I mean, that's kind of the situation of the entire system and to action. So what's really going on now? If I think about individual actuator at one location, right? How possible that I can really have in this global information? So what it says that even I have don't worry about the learning, people tell me that is the best policy you should go ahead to take. This is impossible to really take in that action because it is information, limited information for individual agent. So that's motivate us to think about what the policy we want to learn. The policy we want to learn should be implementable in certain sense. And for the talk, I will focus on the extreme case. That's what's the title of the talk is the localized policy. So let's just learn some local policies. The local policies means for each agent, I would like to know eventually getting a local policy that I can take my action based on I observe locally. And for the extreme case, I just had my own state SI as the policy I want to learn. So I want to say this work can be extended to adding the local policy based on the neighboring information, but focus on the simple case, fully localized policy based on the local state, what we can do. So that's kind of challenge 1, challenge 2. Now let's look at, if my goal is only to learn the localized policy, doesn't mean I can just do the independent learning. So we have been seeing talks in the past days, talking about independent learning and how the independent learning going to evolve. So my argument here is my goal is I want to optimize the global system perspective. So even I only learn my localized policy, but because my state transition still couples everyone together, and that means my local policy will still affecting the entire system. So ideally, if I really care about the global system performance, what I need to do, I need probably still communicate. So that's why the communication come to play is, so what we want to do during the learning is we would like to develop some learning rule, and it's I call it a distributed learning rule. The learning rule should using the local state, every agent using their local state. I put in a quote on the local because we're going to define what local really means. The local state, either through his own observation or his local communication, and the local reward he observed to learn a good local policies. So that's the ultimate goal we want to achieve. And everything's still cooperative. I'm not talking about agent play according to their best interest, to see what we can achieve. So now let's dive into design the algorithm. So when we put into the algorithm, we grab there's so many IO different type of methods. I will focus on the policy gradient in this talk. So this what do the policy gradient? I do parameterization. You can just think about the simplest parameterization you're going to do. Just do the direct parameterization, for example. And the difficulty is how to evaluate the policy gradient if I don't know the model, right? Lots of work is one popular method is to using the policy gradient theorem which is able to just based on the Q-function, which is the expected long-term reward, to evaluate or estimate the policy gradient. So one essential component for the policy gradient theorem is to evaluate the Q-function, which for the tabular case, we can call it as a Q-table. And what that one is, this is a single agent for information case, is if I really go ahead to implement this method, what I need is I need a big joint table that tells me how good I'm doing based on the current entire global state and global action profile. As we talk about curse of dimensionality, like, hey, this Q table is just exponentially large, depending how many number of agents I have. And the system we have in our mind is always really very large scale system. And on the other hand, it's actually also need global information. How can I really have the global information in such good time? So those are the two challenges. Now, let's if I put into the setting, because my problem, the network MDP, do have some structures. So I want to see that for my structure, does that structure give me some benefit? So we put in the policy gradient, like putting our RL, the MDP problem into the setting to see what we have. So we have only want to learn the localized policy. And the localized policy is for each agent, theta I. And everyone, they're taking their own local policies, and the joint policy is the product of all the local policies, right? Nothing fancy here, just like writing down what we really want to have. And then I'm writing down the Q function definition. The Q function is just a summation of the expected reward. And the expected reward is a summation of every individual node's reward. I just put in them and exchange the summation of the order. Then kind of naturally, I will have something can call it QI theta, which is like the long-term expected reward for one agent QI. So the intuition for this QI theta looks nice. That is for individual agent. That's how good my expected long-term reward if I start with SA and taking the policy theta. But the one difficulty here is this individual Q table is still exponentially large. But if I need, because the state transition couple everyone eventually, I need have to know what's going on with the entire system, S and A. The first challenge we look at here, I cannot really proceed anymore. A second challenge is now I'm going to write down my policy gradients here. So now for the policy gradient for each agent, he's going to take the partial gradient of his own action policy theta I. I'm writing down everything, and there's one component. Let me see. This is good, but then for here, because my Q is a summation of everyone's Q. Again, that means I need everyone's information. So both the Q table and the policy gradient tells me I cannot really proceed if I really have a large scale system. So now what we should do? Let me summarize the challenge we have here, right? We had making one small progress is for individual agent I. So you can imagine you are the agent I in the network. So I know the way I should do it to evaluate how good the situation is for the expected long-term reward at the QI. But that one will depend on the entire system, which I don't have the information of other agents. So how should I proceed? I will give you a few seconds to think about your own solution. Now, okay, good. I guess so probably many of you will already have some of your own solution you want to try. And the way, I think that we listen to the independent learner talk, we can probably just treating individual agent I as independent learner, go ahead. I can use some mean field tools if my system might further adding some assumption about the mean field property. And the thing I want to say is something we did is kind of something between the independent learner and the entire centralized learning is I'm not I cannot really evaluate my entire QI for the joint state, joint action. But what I can do, because I can still see what's going on around me. If you think about when you're driving, you actually can always know what's happening nearby, and especially with the Google Map. So now I'm going to just do a simple thing since to the truncation. Depending how much memory I have, depending how much computation I have or how much communication I have, I will just do one truncation based on my ability. And the call is I can change it. That's kind of the local, as I talked about before, the local means. I can define what kind of K-hop neighbor I want to do depending on my ability. So, but this is does a truncation really going to work by just ignore the existence of other agents? The good news is the truncation, just by ignoring others, the existence of other agents, work to a certain degree. Because for the system I'm describing, the network MDP problem has one nice structure, we call it the exponential decaying property. So what the exponential decaying property here says is, so yes, I need for the long-term reward for individual agent, I need to know the entire state an entire action profile. But if one agent is really far away from me, and then the effect of that agent state action only play a small effect. And as the distance getting longer, the effect actually will get exponentially decay. And the rho is a decaying factor. So when I put in the discounting reward case as an example to talk about here, because everyone can kind of think about, okay, you have a discounting reward. So each time, by the time when one agent affects another agent, is already being discounted by the distance between the two agents. So kind of one intuition, but I want to highlight is actually the true decaying factor is much better than the decaying discounting factor gamma. And that's one of the reasons why we can extend the result to the limit averaging case, even without discounting the reward. It still has exponential decaying property for most networks that we have been encountered. So, yes, questions?
What is rho? Like, I mean, in your proposition here, like, okay, like you said, it's more equal than gamma, but like.
Yeah, you said the rho here, right? Yeah. So, like, the question about what's the rho, right?
Yeah. What is the value?
So the gamma is the discounting factor I talked about before. So like by the argument I said before, like definitely, so the decaying was smaller than the decaying factor was smaller than the gamma. And the rho was a real rho here, like as I said, it's a consequence of the net structure, discounting factor, and also the mixing rate of the MDP. And we do not have a concrete form for the rho, but like through all the numerical simulation we have been seeing, like for many cases, if we just random generate your network, the rho can be substantially smaller than the gamma. And the rho, what here means, it just means how fast the exponential decaying is. So the smaller the rho is, the better. If my rho is really, really small, that means I can basically ignore the existence of other agent. But if my rho is very close to 1, so here is a smaller than 1, equal to 1, that actually means the truncation, the quality of a truncation is not going to be that good. And if my rho is very small, I can pick very, very small k-op neighbor. Does that kind of answer your question? But so far, we still don't have the like analytical form about, hey, what's the better like bound for the rho.
Yeah. Sounds good, yeah. Thank you.
Also, I would like to ask one question. Why we're trying to compute the gradient via the Saturn's Q-function, and we don't try to do reinforced estimator?
We do not try to do what? Can you repeat the last?
Reinforced estimator.
I still couldn't hear clearly. Can you why not to?
What's estimator?
I mean estimator, right? So, as I said, like, so put it this way. First of all, when we start this one, we were trying to the actor critic framework. We kind of using the policy gradient, and the policy gradient, like, haven't really even talked about, like, now this part is only about the Q function. It's
So I think what the question was it was specifically like, so there's different versions of the policy gradient theorem, right? So you wrote down the one that has like the Q functions. Yeah, there's also the one that just involves like the realized rewards, right?
Yeah,
which is sometimes called,
yes,
reinforced.
Yes. Yeah, I know. Yeah.
Okay. Cool.
Yeah. Right. So the policy gradient, like I said, like first of all, for here, it's only related to the Q. So it's not to do with whatever policy gradient we're going to do. Like even for doing any other Q-based method, this one probably still is needed. And then back to the question about like the policy gradient, right? I can do some other estimation, like for example, the zeroth order, this kind of way to do it. And then another difficulty is kind of back to, even if you're doing it, everyone, I assume, like for the setting, everyone observe his own local RI. And my objective is I want to maximize the joint reward. So no matter what kind of way we're going to do, we need to figure out a way to estimate the global reward. And like indeed, actually, we have another paper on a different setting, like on more like on the continuous state, continuous action space. And for that one, we actually did some other way to estimate the global reward. It's not through the truncation. Yeah, but either way is unavoided. Like we need to figure out a way to estimate, and the estimate is not going to be accurate because the like scale of the system. Yeah. Does that kind of answer the question?
Yeah, that makes sense.
Okay, great, thank you.
Got a thumbs up also. Oh wait, I think there's one more question. Let me move the mic over here.
It's a very small one, but can you explain again what S prime and A prime is here? Because maybe.
Oh yeah, okay, that's good. So sorry. So like for the notation wise, so here, like This is means the k-hop neighbor. Do I have that
Yeah.
one? See, like this means k-hop neighbor.
Mhm.
And then this means like all the agent that is outside the k-hop neighbor.
Oh, so you have the neighbors in the left one, and then the neighbors outside.
Yeah.
Okay,
Like I
okay.
cannot differentiate this neighbors, this not
Okay.
the neighbors. And what it says like the people, like the prime means for the people who are not my k-hop neighbor, no matter what he did, has a very small effect on me.
Oh, okay. Thanks.
Yeah. And that's one of the reasons why we can do truncation, because it doesn't really have much effect.
Yeah. Okay, I see. Thank you.
Okay, great. Thank you for the questions. Okay. Now, like, look at back to the Q function. So I said, now we did the truncation, and the reason why the truncation worked because exponential decaying property. So like we're kind of solving kind of one challenge, like for the joint Q table. Even though if you don't do the policy gradient, doing some other method, probably you can apply this kind of way and to adding performance guarantee on the quality of the Q that we would like to have, like the truncated Q function. And now back to the gradient. Right, I said multiple way to do the gradient, and we like for this paper we did this policy gradient. So the full policy gradient is when we writing down, right, just writing down the partial gradient, and partial gradient is like summation of all the long-term expected reward. So we kind of figure one issue out is we did the truncated one, and that is okay. But then this has the global summation. How are we going to do that? There is a technical proof is. Turns out if I already started with the small truncated Q, actually when we really go ahead to rewrite the policy gradient, we actually don't need to do the summation of the global summation. We just need the local summation. And like whatever showing in this truncated Q table, then keep that one as a neighbors. So that's actually another benefit, like by at least for this part, if I go ahead to truncate my Q and then so like it happens, then my policy gradient, I don't need to do the global summation. I only need the local summation. Putting all the things together, so it's ultimately what we did is we put in a one good way to estimate the global policy gradient, and we can ensure the quality of the gradient estimation. And how good the estimation will depending on the decaying factor, and like also how many neighbors I will pick, like k-hop neighbor. If it didn't do good one, we probably should pick in a larger one. So any questions? So now you can see like if I have this two, yes.
I would like to ask one question. It is more related to the question of cost is, do you have even some heuristic that you can describe about some specific structures of networks that can describe the rho? Like if I have a cycle, you can tell me that rho is something like 2 or 1. Do you have even heuristically just to get some idea about the different networks that someone can see?
Good question. We got that question for like every time when we talk about this work. So previous way, let me talk about the k-hop neighbor. So first of all, the result is general. Like you can be a line network, can be like fully connected. That means you actually including everyone's information. Can be any other kind of network. You can have a cycle in the system. That's also okay. And k-hop neighbor. So far, what we like have or defined is really means if two agents like from the link, and you can look at my link right now is you through the definition, like you put in the hop of neighbor, as long as if any agent that is belonging to the k-hop neighbor, then that one should be included. So in the extreme case, right, so people have the complete connected graph, that actually means every agent will be included. So like if I really want to say this one can bring down the complexity, this means I kind of already underlying assuming the graph should be relatively sparse. Otherwise, I don't have much benefit because the k-hop neighbor probably for some agent, if there's a one agent kind of connected with everyone, for that agent, he actually will including everyone's information.
So from theoretical computer science perspective, if I give you an expander, for example, can you somehow estimate how much is?
Yeah. So
you want the opposite of an expander, right?
Oh, right. Yeah.
Yeah, and one thing I want to highlight is this, because we didn't make further assumption of what kind of PI, like the local state transition we're going to do, but the rho factor here, well, depending on the network structure, but also heavily depending on the PI, the state transition probability.
Okay.
yeah, that's why it's becoming complicated to like just putting a nice thing to say, hey, if I have this graph, what will happen? This graph, that happen. But what something we didn't try is probably if I kind of start with, hey, about the PI, if you have like K agent is has a K degree, and then automatically your PI will be like upper bounded by 1/K. We didn't do those things, and that's why we don't have the characterization of the role. But if we're making further assumption of what kind of PI will and how the PI is scaling up with the network, that probably some result can have. Yeah, it's good. So I will go to the next slide. It's already 30 minutes. Sorry. So, but thank you for the questions. Now, like you can see what we can do is just like putting all this in together, right? You can learn the truncated Q function using the local information and do the truncated policy gradient. As we already discussed, I said like the exponential decaying is not really tightly tied with the policy gradient. So if I do the Q learning method, I can use this similar method to the Q learning, but figure out the way how to update the Q. But we didn't try those methods, but something we want to try, I think inspired by the talk about V-learning by Chizin. For something we can do is do some like the V-learning type of thing that I can totally just get rid of the dependence on the A. But that's just some idea recently when I listened to the talks through the workshop. Now about the performance guarantees, I still want to spend 5 minutes to talk about something I found that's very interesting and a connection with all the games. So now the performance guarantee we have, like it's kind of quite standard. I think like this is the episode. So from the learning, like if we do the active critic method, have the 2-time scale. So this is kind of the episode M. So this is the episode. So it's 1/, it's the growth of M. I think kind of consistent with the learning result for the centralized case. And then this is the arrow because I did the truncation. So that no matter what, I cannot really make this one be like converge to 0. So it's always a arrow. Introduced by the truncation. And one other thing, I didn't show those polynomials, but just kind of you guys should believe me. So all these polynomials will just depending on the size, like the state action space size of the K-hop neighbors. So it's like there's no term, the size of the network N is not going to show up in those polynomials. And that's kind of the goal of we want to do from the beginning. So we want to have some algorithm that's kind of can like scalable to the large size of the network. And this is a theoretical guarantee. We had a simulation, and given the interest of time, so I'm not going to talk about too much, but I want to highlight. So the connection of what we did with the independent learner, because we listened to some talks on the independent learner, is like by making the K-op neighbor to be 0, like don't using any other neighbor's information, just use your own local state reward, like to run to see what's going on. And we actually simulate those algorithms. Indeed, if by doing that will be actually better than like this is some benchmark algorithm. So if I have time, I'm happy to tell you a little bit more what we did for this example. But as I mentioned earlier, I said we actually had some other setting because this setting was okay to model something related to the like networking or wireless communication, which like we can say the state action probably is kind of finite, or you have a like 1, 2, 3 you can countable. And we had some other like collaboration, like we was asking us about the like, continuous space. And we can also not really making the assumption, say the reward is bounded. If you think about LQR case, right, the cost function is never going to be bounded if I don't have any other assumptions. So we actually had other settings. And for other settings, I'm not going to talk about details, is we indeed, like we have a different way to estimate the gradient, not the way I was showing to you before. And there's one challenge I want to highlight for when I was working on this problem is actually the stability guarantee. If I don't really assuming boundless, and then is what happens, my state will go into the dangerous, the unsafe region. So we had like through the way design, like the way of estimation of the gradient to kind of overall to ensure the stability of the learning. So if you're interested, I'll refer you to this talk. But now I will spending a few minutes to talk about something I think for me, I found it's very interesting. I kind of finally clear my soul like what exactly going on. So I talk about like our multiple goal is for the cooperative setting, maximize the global reward. But you can see like the result is only in the stationary guarantee. So we asked the question, what exactly this point are? So we studied that question. And so then in the meantime, then we find Agowast's paper on the single agent type MDP case. Like for example, for direct policy gradient, the stationary point is actually equivalent to the optimal point, which is very promising or like encouraging when we read this paper. And also because the underlying property for the single agent, it has a gradient domination. So for our case, we only have one agent. I think our algorithm just becoming a policy gradient like this paper. So then we want to see like what happened for our case. We had two things, and we run some other so this is actually the other simulations. Indeed, depending on the initial point, we will have a different value. So that means it's definitely not really global optimal, and there can be so many points. So and then we look at what exactly going on, what exactly we do for our problem. So this is the back to this picture. So I want to say two things, two differences compared with centralized learning. So one is even you have a single agent, I think what we kind of forcing ourselves to do is the partial observable system. Every agent just taking the action based on his partial observation. And we know the Paul MDP is challenging. That's probably what making the optimization landscaping harder. And then another thing is here, I kind of assuming every agent taking their action independently, right? So kind of like the decentralized policy, the independent agent. So these two are kind of fundamental differences compared with a single agent. So then we look into we kind of separate the two challenges to really working on understanding whatever I talked about before is super challenging. We don't know what the starting point. So we kind of break the two challenges. First, do some POMDP, not POMDP, like the partial observed LQR study, what we can have. And then we also look at the tablet MDP for the independent learner, what we can have. So as I said, I really want to share this one. Is probably is obvious for many of audience here. So I will try to finish in 4 minutes by telling you some things I found that's interesting. So now actually I went to the extreme case. I said I didn't do game theory at all. It's fully cooperative setting. So now I go ahead to making my problem relatively easier compared with the problem I talked about before. So now, okay, let's forget the state is local state. I can allow them to share the state, but action is still going to be the local action. And state transition, this is state transition. And because now I only kind of think about the one joint state everyone can observe. And also for here, right, since I talk about cooperative setting, just global objective, I just put in the global objective to everyone's reward. That's kind of the multi-agent MDP setting. That's what I did before. Is everyone want to solve the global one? I even assume they have the global reward and want to maximize it. And now I only keep this feature. The feature is decentralized policy. And now the policy everyone going to take is the joint policy. So I think this is very similar to the talk we listened this morning, and also in the past 2 days, we had the stochastic games, right? The only difference is now I'm just doing the identical interest, putting to be more like cooperative setting. So we can do direct parameterization, we can do softmax parameterization. Let me focus on this one to talk about something interesting I found this. I recently think is interesting. So now the question, as I mentioned, right, just now under this simple setting, but not very complicated, there's no conflict, and run the policy gradient. And I didn't talk about how to do the sample-based gradient. Let's say even you have the gradient, right? What's going on? So the policy gradient, at the best, right, what we going guaranteed is going to reach to a first-order stationary point. So this kind of equivalent point from this learning dynamics. And now, what's exactly this stationary point? So definitely we know it's not optimal. I already showed that we run the different simulation, you will have different point. And one good news is that's kind of connecting back. Even I start with a cooperative setting, now it's actually the equivalence is the stationary point is equivalent to the Nash equilibrium because the information constraint, I didn't allow them to coordinate when they're taking the action, even though they share the same global, share the same reward function. And so when we look at this one, first, I would say we think we had a nice result because now I know what the stationary point I got, right? It's going to be Nash equilibrium, which is I feel, oh, now I know what's the point. But then after second step, right, and this actually tells me this method actually not really working very well because even for the simplest setting, that's what we end up. And we know from all the talks, right, the Nash equilibrium is non-unique, even for the identical interest case. And the quality of Nash equilibrium can be very poor. And what's really happening, if I just run this algorithm, I kind of change my cooperative setting to becoming non-cooperative. I don't have an answer to solve this, That's why I say it's interesting, because putting me into thinking what we can do. So like in just like last minute, I want to just say is the result from here, the equivalence, is not really unique to the identical interest. So this morning we had a talk from Yannis talking about Markov potential game, which has another structure about potential function.
Question. In the identical interest setting, do you have a convergence rate for this?
Yes, we have. Okay. We have yes and no, but we have a convergence rate for the first order decision point. Okay. Yes, Nash equivalent. But we don't have these questions. We don't have the quality of the Nash equivalent. This one, yeah. But we have
2021 paper.
Yeah. It's a different paper. So I will in 2 slides you will see it, and almost.
Thank you. But we agree that in principle it is like non-convex distributed optimization.
Mm-hmm.
If we have if we apply just gradient play in that identical interest case, and I have an exact estimation of the gradient, then what I am applying more or less is non-convex distributed optimization, right?
Yeah. You have a very good point. So the thing that's why for here when I say it's kind of on certain degree is actually good news, because like if you just have a general non-convex problem and Nash equivalent to the first order decision condition, this one will be okay. But then the other round is actually harder if you don't have any structure of the fee. So the reason why it's actually equivalent is because my fee is actually coming from my long-term reward for my MDP problem. And so this morning, Yannis talking about why is from the MPG. I will have like 2 slides to show you. Like this is not a random just like one common like ordinary non-convex optimization. This is a fee. It's coming from the reward function from the MDP. It has a structure once I do in the direct optimization. Yeah. But you was like just 2 slides. So what I want to put in here, the equivalence is. Since I don't have any progress about cooperative setting, then actually I go how about just like non-cooperative setting from beginning? So every agent can have a different reward, and every agent just want to maximize their own reward, right? And in that setting, it's kind of like the stochastic game that's like proposed originally by Shapley, and it's kind of consistent with the rest of the talk, other people's talk talking about stochastic game. So the first order stationary condition is actually equivalent to the Nash equivalent, even for the general setting. So basically, the slide I showed you before, that's what has nothing to do with identical interest, right? You want to have a cooperative, it's just becoming non-cooperative. And like I want to highlight this actually for general, I don't need any other structure. As long as it's a tabular stochastic game, then I have this equivalence. So it looks good. And the reason, so now back to the reason why I say it's not ordinary like non-convex optimization is the gradient domination property. So I don't have time to go to the details. This morning, Yannis from the MPG describing what the gradient domination. I want to highlight is the gradient domination for this property is not just like it holds for the general stochastic game. I don't really need a potential structure. So this one holds in general. So, but then where I really need some structure, like the identical interest. So now back to the question, like, do we have a convergence rate for those problem? Yes and no. No means if I don't have any structure for the JI, I don't have. Like we listen to the talks, we have a Noah talking about complexity of the equivalence. And like this is not really learnable. If I have algorithm, have convergence rate, then it's great. No. So for the general game, I don't have. So there's no global convergence rate for the general stochastic game. They can be cycling because those kind of JI, like it's not going to be consistent. Like for the zero sum, you have some structure. For the general sum, like hard to know. But just like 1 slide to summarizing some result from 2 papers. So what we can do is this. So for the general case, what we have is we can study some local geometry of the Nash equilibrium. And this is kind of like, I think from the nonlinear dynamics point of view, right? I have a dynamics system, so I can go ahead to study. I know the Nash equilibrium is kind of one of those equilibrium points, and I can go ahead to study the stability. And we have some result characterizing some Nash equilibrium for the local geometry. Now back to the identical interest. So the identical interest, like, is they didn't play a role in showing the equivalence between the stationary point and equilibrium point, but they do play a role to help me to study the convergence, because now my J is just 1J. I can use it in the gradient accent method to study the convergence, and we can have a convergence rate. I want to highlight, right? It's just say converge to one Nash equilibrium, which one is highly depending on the initial value. So, and then we can go ahead developing sample-based method. So yeah, Yannis for their paper had a model-free method, and we had some like model-based method. So far, our convergence rates are being consistent, and I know like there are some other extension improvement on this line of work, and we also look into like the softmax policies, because for the work I talked about first, we actually did a softmax parameterization for that localized policy. So we look into what is happening for the softmax policies. The message is more complicated. I'm not going to talk about here. Is in our recent paper, should be 2022, not. So now I want to say, yes, please.
One quick question about the results. The local convergence is about the exact gradient.
Yes. Sorry. Yes, the local convergence is about the exact gradient. So we didn't really do the sample-based method. And one thing I want to add is like strict Nash, for example, this result is because it's kind of quite stable. When I say quite stable, it means it has stability margin. Like has my background from robust control, so like I always actually like the epsilon arrow here, even no matter whether it's sample based or some other way. So it's actually for some result, if you add in some perturbation, I'm not talking about sample based, they can still hold to some degree.
I understand.
Yeah.
I have a clarification question.
Yes.
So in the previous slide, you had this gradient dominance property, which made it seem like any stationary point is a Nash, global Nash. So now you're saying you can't converge, like I don't understand the left-hand side of the slide, given the gradient domination theorem.
So, good question. Okay, we got those kind of questions from the reviewer as well. So when I put in the gradient domination, you look at here, this is actually putting a quote on the gradient domination. It's not as nice as the gradient domination, like the single agent, right? You have the optimal, you have a global unique optimal point, and you can bound the difference between the J theta with the J theta star. And look at this one. This is the kind of fake gradient domination. Is for every kind of the theta I minus I, and then like this is everything, and then this you can pick one being the best action and to compare. So this one and also those kind of measure will change according to where I am. So the proof when we have like kind of the Nash equilibrium gap, and the Nash equilibrium gap is defined that there's no point being fixed at anywhere. So that's kind of one of the difficulty. And then this is actually this is actually from the normal form again, right? And the reason, because if I overall I want back to want to highlight this one. Another thing I want to highlight here is the JI, right? For each agent JI, I have some of this kind of property, but I don't have anything saying like globally, like because every theta I they're going to change, but what happened for the global system, I don't have that. That's one of the reasons, like this kind of is that kind of gradient domination is not really ruling out this kind of cycling argument. And that kind of also one of the reasons why I say for this part, right? Why this one, why those going to work? Because now I don't talking like I really have like a little bit more real gradient domination. I have the kind of same J to talk about how the gap between the J theta and the J theta star.
So then could you convert to global Nash if you had taken your reparametrization to be shared, like the parameter to be shared by all players?
So I don't have an answer for this question yet, because I think like how to parameterize the policy like among share. I can't even, yes I would, because I would listen to the talks. I think people come, Noah and Chijin, right? You guys have a different way to say the policy pi and extend to the CCE the things. And I don't know. So for my setting.
I guess the reason why I'm asking is because I didn't totally understand. Because you see, it still seems like you have the first order equivalence with Nash. I didn't totally understand your point with the gradient domination thing, but I think it had to do with just one player's things do not match each other's.
Yeah. Right. So because here this gradient domination, adding a quote here, is for every agent you have the Ji minus Ji, but then everyone's Ji they can be not aligned at all.
Okay, that makes sense. Cool, perfect. Thank you so much.
Okay, that's why like, if I talking about equivalence, that's enough, because the equivalence really forces this one equals 0.
Okay, awesome. Yeah, that makes sense.
Yeah.
I think we should wrap up.
Yeah, okay, good. So I already wrap up. This is my final slides. So what I want to say, this is the most important one. I really want to solve this kind of societal system, and then have an information communication constraint, force me to do the localized decentralized policy, and then kind of naturally like emerges from my algorithm, kind of policy gradient, stationary point we want to study, and then happily becoming Nash equilibrium, and then becoming kind of non-cooperative setting. And then lead us to think about these questions. Is we know like for the normal form games, a lot of studies talking about POA, price of anarchy, price of stability. If this one are bad, like if I have really bad Nash equilibrium because I cannot guarantee which Nash equilibrium is converged to, then can I redesign my tuning function like adding tags or regular? I think from our RL society, you guys probably like using the regularizer language, right? Kind of using a regularizer to kind of shape what's the quality of Nash equilibrium and what kind of not the convergence rate you look at here. I just want to shape what's the point converted to. In a more general setting, I put it this way, right? There are many other learning methods, and they are for the characterization of the learning dynamics. This is like one way, turns out to be the Nash equilibrium. What about other things? And eventually, can we really come back to do some real application for the societal dynamical system? That would be very exciting. So thank you, everyone. Thank you for all the questions.
Thanks a lot. Yeah, in the interest of time, maybe if people have more questions, they can ask Lena offline. So why don't we just have like a quick like 2 or 3 minute break to give Dorsa time to get set up, and then we'll go on to the next talk.
Great, thank you. I will stay here also for Dorsa's.
Thanks again.
Thank you.